So I'll end there. Thank you. Yeah?
What initial state was it you explored? I mean, what constraint did you have between the system and the domains?
Oh, you're asking the initial state of the system in the apparatus? Yes. So I started it in a, so what I started it in, I guess this won't show anything, but I started it in a superposition state when you're comparing it to the computational basis or the Z basis if you'd prefer. So it's in a superposition state with non-equal terms adding the two. So it's like the state I wrote earlier, starting in something like this.
That's zero on both sides.
Oh, sorry. Thank you. That would be not as interesting. So yeah, so non-equal values in the superposition.
And why the six qubit for the environment?
Oh, I suppose just as something to try. These ended up, when all is said and done, these took a while to run. I can still optimize it more, but it was just as a sort of a choice. I wanted the size of the environment to be bigger than the size of the system. So I could have gone with 4 or 6 or 8 or arbitrary, but there was nothing special about the value I chose. Yes?
The spatial location of it isn't significant either, right?
Yes.
The 3 on each side or something.
Right. I originally wanted it to maybe have this sort of description, but after just sort of trying different things, I ended up with a fairly non-local description. I still need to, it's fairly easy to reverse engineer the Hamiltonian. I still need to analyze more exactly what it means as a fairly large matrix I have to sort of sort through.
The energy eigenvalues you just have, or the eigenstates you have a bunch of zeros with a single one. Maybe if you make it a domain wall, like a bunch of ones and then a zero, you know, a bunch of, like, so instead of tracking the position of that one, track the position of the domain wall, then it might be a more local Hamiltonian.
Oh, so yeah, so that sounds like a good idea. Okay, maybe.
Because this almost looks like a single particle type of.
So this is just how I'm actually sort of writing it out. So this decomposition goes in terms of all 256 of them. Yeah, so it's actually the.
It looks like he's only got one of them on one, but the next term that he didn't write would end in 1, 1.
Okay,
yes, so I actually had all of them, but maybe I could tweak it like that and get some more local looking behavior. Yes.
So how are you thinking about the relationship between line selection and the arrow of time?
Good. So at least in, okay.
So in perfectly maximal entropy, any state's an eigenstate.
Yes.
There's no pointer, special pointer basis.
Yes.
So there's that piece.
Right. And I'm never, a thing that slightly disrupts the perfect degeneracy a little bit is you see it never quite settles down, which is, probably partially an artifact of the size of the system, but I'm sensitive enough to sort of see that it never quite settles at maximum entropy, which disrupts the complete degeneracy in the choice of eigenstates a bit. I guess I'm not sure exactly you were asking this, but I will say when you
think there are pointer states in equilibrium.
I'm not sure of that. I don't think so. I think my analysis so far, just looking at the diagonals and even looking at what the preferred pointer basis is, I think is insufficient for that. We can maybe talk about it more later, but I think part of the issue is when you can't sort of unambiguously say a measurement happened in this basis. It might sort of get disrupted enough where you're unable to really have some nice consistent picture or able to describe things using classical probabilities for a long enough time scale. But I need to think about that more. I don't know if this was part of your question, but something I guess I left out. You don't see it here, but maybe as you'd expect, there's sort of a double-headed. I didn't talk about the arrow time that much, but I think Andy mentioned it or explained it at least last time, where you have an arrow of time when you have increasing entropy, and so just like how you'd have, you'd say, this explains the time asymmetry we observed despite time reversal symmetric dynamics. You would see we observe time only going one way as opposed to the other because of the arrow time, because of entropy increasing. You can just as well say on this side, it looks like you would have a description looking like time increases that way. And if I followed, if I went through this sort of backwards, I would see you'd go from something that doesn't have coherence to then sort of a coherent superposition state popping out. And then when you got to the other side and you had the other direction for the arrow of time, then you can have it decohering again. Maybe not demonstrate as well in this one, but it's definitely true in the previous state. I just didn't draw the other side of it. Oh, go ahead.
So in real life, a measurement apparatus is this finely engineered thing that people work hard and spend money to make nice. What's special about your I couldn't tell what you'd done to make your apparatus an apparatus.
Good. And maybe a very inelegant way, sort of trial and error, I'd say. So it's
an apparatus built by a theorist.
Yeah. Yeah.
But is there something special? I mean, have you done something? I just couldn't tell from the presentation.
So I can't see. I've not actually explored whether or not a measurement's happening. I'm just looking at whether or not.
So you're not really addressing. So you
not yet.
The system and apparatus, but you haven't really.
Not yet. Yeah, I would like to do that. And I think if there's good reason to say Boltzmann brains, there's some reason they're not good apparatuses, or in some models they aren't. Then maybe that's something. But okay. Yeah, I'm not. I can't quite answer that yet.
To discover good apparatuses.
I hope so. Yeah.
Or not.
Sort of in a blunt, just try things sort of way. But yes, maybe I'll get smarter and think of a better approach. Was there another?
Yeah. Have you tested how the off-diagonals look like if you take as a basis the one that you get from the infinite time average of your initial conditions?
If you do the infinite time average.
It would be something like the equilibrated state of these initial conditions in this closed.
Well, the full state doesn't ever really equilibrate.
No, but this is why you look at the infinite time average, right?
Well, you just go
I mean, the 256 time average.
Yeah.
You just take average over one cycle.
Sure, but then you could look at this state.
Yeah, so it will be some state, right?
Yes.
Do you, does this represent?
Yeah, I'm not, because I don't have sort of, I could do a average over a full cycle. I haven't thought of doing that. I don't know necessarily that, I guess in some way it's giving you average behavior. So it's something I haven't looked at, but it's, maybe I'll try that.
So you're really trying to focus on brief moments and asking in those moments that have an arrow of time, what's pointer basis being selected, and ultimately is a measurement being made?
Yes.
Okay, but you're letting the system kind of bubble these things up, and,
yes.
and you're just watching them and checking for what comes out.
Yes, I very much like unitarity, so I want to fully embrace it and not have some effective description where I'm not keeping track of everything. So I'm letting these fluctuations sort of pop in, sort of. It's hidden in the full detailed description, but you sort of get this effective type of fluctuation. Yeah.
Well, I think that it sounds plausible, or maybe true, that not all Hamiltonians will give you decoherence or classical behavior. That we usually experience that if there is some locality of the Hamiltonian, which your thing didn't really have.
Yes.
Yeah. So it might be that that to get the kind of what we hope is typical behavior, you need some more structured Hamiltonian for the system, or the bad.
But the thing I like about the spirit of this, whether it works, I don't know, but is you can ask, are there different, if you have a random Hamiltonian, are there different ways of splitting it into a system that start looking like that?
Yeah.
And so you can ask, does hidden somewhere in some random garbage, is there a classicality of origin if you look at it the right way?
Yes.
And that's actually different than, so I'm very interested in that question, but the result, the work I showed on Monday was highly engineered because I was trying to really make decoherence as I know it happen and then ask some questions about equilibrium. But
This is the complementary.
yeah, it's complementary, and I'm really interested in that.
Yeah.
Thanks.
As well. Yeah.
Okay.
Okay, so
Can I have one last question?
Oh.
Very quick.
very quick.
In the plot, entropy versus time, like for the time, I guess we have some rough idea of like the scale. But for the entropy, do we know like the actual value is plotted on the or
Other than the minimum and maximum value, or?
sorry, the entropy versus in the black hole business.
Well, my plot is not very precise, but yeah.
Is there any scale on the entropy axis, or maybe per unit volume or?
Well, so I'd say when trying to describe and account for the observed universe, I'd say there is sort of appropriate scale. I don't. Do you know the numbers? I don't have know the numbers off the top of my head. This was meant to be sort of a general sort of look where you could have had this just be me or had this be the observed universe or whatever your best account for everything is. But I think there are good, they're good enough sort of descriptions where you can sort of describe this in the right way to give an actual value.
I was spacing out, so I missed the question.
Oh, he was asking, is there an actual number to assign to this?
To the entropy today?
Yeah.
Yeah, there is. It's 10 to the 95.
There you go. Yeah.
Nits, right? Or nats.
Kilograms. The entropy is dimensionless.
Less than 10 to the 122.